Okay, so last time we talked about linear interpolation, and the main reason, thermodynamic reason, that you would use linear interpolation is so you can come up with values in the table in between values that are given. By the way, I didn't say this like explicitly, but if you look at the formula, it kind of makes sense. So you can use linear interpolation to get usually a pretty good approximation of things between two values, between two x values, independent variable values. There's no way using that formula to get values, say, outside of all of the values you know. Anyone know what that term's called? You could almost guess. You could guess. Extrapolation, yeah. And that's really hard to do accurately. It's sometimes you have to try to do it, but so interpolation means between the two values that you're given. Okay, so we're going to do one of these. Oh, whoops, I wrote down two of them. We just want to do number 2. So this is so we're given a function of two variables, and we want to evaluate it at x equals 4, y equals 10, and we're given these values. So let's say f of 3.5, 9.5 is equal to so we're going to plug that into this function. So 4 times 3.5 times natural log of 9.5. And so this value is 31.52. And then f at 3.5, 10.5 is 32.92. And then f at 4.5 9.5 is 40.52, and then f at 4.5, 10.5 is 42.32. Okay, so I'm going to go my step 1. I'm going to say f at 4, 9.5 is equal to f at 3.5, 9.5 plus f at 4.5, 9.5 minus f at 3.5, 9.5 divided by 4.5 minus 3.5 times 4 minus 3.5. This is obviously an approximation, so this isn't going to be exact. And then f of 4, 9.5, plug these values in. So we have 31.52 plus
40.5. For 4.5, 9.5 is 40.5.
this is, instead of 4.
40,
Yeah, thank you. $40.52, right. Okay, so 31.52 plus 40.52 minus 31.52 divided by 1 times 0.5, and we get, so that is just 4.5 plus 31.52. So I got 36.02. And then step 2, we're going to approximate the function at x equals 4, y equals 10.5. So that's f at 3.5, 10.5, plus f at 4.5, 10.5, minus f at 3.5, 10.5, divided by 4.5 minus 3.5, times the quantity 4 minus 3.5, and so that is 32.92 plus 42.32 minus 32.92 divided by 1 times 0.5, and that is 37.62. And now step 3. Now we're going to use the two values we just came up with. So f at 4, 10, we're going to approximate as f at 4, 9.5, plus f at 4, 10.5, minus f at 4, 9.5, divided by 10.5 minus 9.5 times 10 minus 9.5. So that is 36.02 plus 37.62 minus 36.02 divided by 1 times 0.5. And that is 36.82. So for this particular function, where we know the underlying function, how close was that approximation? So we can just plug that in as, so F at 410 is really equal to 4x natural log of y. So 4 times 4 times the natural log of 10 so 36.84. So in this case, we got a really good approximation. The quality of the approximation always just depends on how close to a line the function is between those 2 points. If it's a line between those 2 points, the approximation is perfect. And just generally speaking, you get better results as you pinch your 2 points closer. So if your two known values have x and y values closer to the one you're looking for, you get better values. Okay. And that's sort of the principle of numerical calculations. If your approximations have your values spaced way apart, your approximation isn't as good. If they're spaced really tightly, then your approximation tends to be pretty good. Any other homework questions? Yeah. Number what? This is number 2. Okay.
Number 4.
4, sure. Okay, great. Okay. Otherwise, I was going to make you guys arm wrestle.
Is it okay if I just use the Whisk website for that one? Did we have the? I think there was a spot on D2L labeled tables.
Yes, there is a spot on D2L labeled tables.
We have to use the one that was ranked by temperature one and pressure.
Yeah, I mean, yeah, I guess I should have mentioned something about this before. I mean, really, the idea is to just get a little familiarity with how to answer these questions with the tables. But okay, so determine the specific property at the indicated state. Locate the state on a sketch of the TV diagram. All right, so the TV diagram looks like this. And then remember, there's always the vapor dome, it's called. It leans a little to the left. You can do these sketches without that, but what? Yeah. So, and the reason it leans to the left is because over to the left of this vapor dome, it's a liquid. And remember that liquids don't change their specific volume very much. They're basically incompressible. So this line is very close to vertical as you increase energy, and then it'll go something like this. Okay. All right, so water at a given specific volume and 3 bar. So determine the temperature. So what you can do is you can go to the saturation table indexed by pressure and find out if that specific volume is in between the vapor specific volume and the liquid specific volume at that state. Okay, so let me write this down. So for A, look at the saturation table indexed by pressure. Is the specific volume between the volumes that are given for the liquid and the gas? Okay. If it's between those, then it's some kind of, I mean, if it's exactly one of these, if it's exactly the liquid specific volume, then you know it's at the saturation and it's a saturated liquid. Okay. If it's exactly the one for gas, then you know it's it's at saturation and it's all vapor. If it's in between, you know it's some combination of those two. Okay. If it's less than VL, if it's less than either of these, then it's going to be a compressed liquid and you're going to have to switch to the liquid table. Okay. Well, in this case, you don't even have to. You've already answered the question. You know it's a liquid with its temperature and pressure below the saturation point. If the specific volume is higher than the one for the saturated vapor, then you know that it's a superheated vapor. Okay, it's not at saturation. Any questions about that reasoning?
Because it's 0.5, that's why it's
in between the two. I think the volumes are like 1.07 times 10 to the negative third for the liquid and 1.6 for the vapor. So yeah, that's 0.5 is between those two.
0.5, yeah, right. So let me just go to the table and the pressure that's given is 3 bar. And so let me just go through 46 clicks to get to D2L, and then we'll be right on it.
At least they don't give you the two-step verification every time you sign back in.
Yeah, do they do for you?
Yeah, I have to get a text to my phone and confirm it.
Oh my God, that's horrible. Okay, so this is water, and we want to look at saturation to start with. Indexed by pressure. We're going to go to 3 bar, and it's given in bars, so that's right here. And we'll go to specific volume. So yeah, the saturated liquid. Okay, this is a very weirdly the way they kind of word it or whatever is strange. So they're saying that the value they give you is the saturated liquid value times 10 to the third. So you might think you multiply that times 10 to the third. It's actually the reverse of that. You multiply, this is the value times 10 to the third. So the value is 1.07 times 10 to the negative third. Okay. And then, so that's less than 0.5. Now we'll go to the gas one. That's more than 0.5, which means that some combination of some amount of liquid and some amount of volume together will give you that specific volume. And so so let me write, so we have 1.07 times 10 to the third is less than well, it's less than 0.5, which is less than 0.6. Anyone remember what that value was? 0.6 something.
6058.
Okay, I'll just call it 6.1. So this is a saturated mix. And so if this is if this black line there is the curve for 3 bar, our value is somewhere in here. Okay. Then for oh, and we have to determine temperature, I guess, too. Oh, well, it's at saturation, so that makes it easy. Right.
6 degrees Celsius. Yeah.
Right. So since this was at saturation, we know it's at the temperature of 133.6 Celsius. Okay. So now ammonia at negative 30 degrees Celsius, and X, the quality, is 0.5.
That means it's at saturation, right?
Exactly. Anytime you talk about quality, you're at saturation. Quality doesn't have any meaning when you're outside of saturation. So maybe someone would argue quality of 0, you could be a superheated, a compressed liquid. At quality of 1, you could be a superheated vapor. But there's no point in talking about quality at all if you're not at saturation. So quality equals 0.5 means that this is at saturation. So again, we're in here somewhere. And we want to determine specific volume. Okay, so for that, we need to look up the specific volume for the liquid and the specific volume for the gas. This is ammonia at a temperature of negative 30 degrees Celsius. I'm going to use the saturation table that's indexed by temperature for ammonia.
Are there any there's refrigerants listed in water ammonia used a lot in thermometric bag applications?
I just put in the ones that occur in the calculations that we do. Yeah, so the refrigerants are in there because when we do refrigeration cycles, those are standard things that you use. I'm not sure why ammonia, but that just comes up in a couple of problems. Water obviously is the most important substance in this class. Did you know that? So we're going to talk about power cycles, and the power cycles we're going to talk about are steam powered cycles. And you might kind of think like, oh man, what's in today's day and age, are we really talking about steam power? You're picturing people in, funny hats shoveling coal into a train, But yes, most power plants, the working fluid in the power plant is water. Nuclear power, the working fluid is water. It's steam. You use the nuclear energy just to change the temperature of the steam, And the reason that steam is useful is because, well, it's a pretty accessible phase change temperature and pressure, and it's very abundant, And so it works perfectly fine, What?
And safe.
Yeah, that's right. That's true. Yes.
And it also has the highest specific heat capacity too, of basically anything.
I don't know. Does it? It does have a high one. I don't know. Yeah, I don't know how it compares.
Really
Okay. We should look that up sometime later. Okay, so we are looking at ammonia indexed by temperature. So here's negative 30. Our specific volume is 1.48 times 10 to the minus third, and then 0.96. Okay, so we got 1.48 times 10 to the minus third in SI units, and then 0.96. And so now to get our specific volume, we're going to go 0.5 times the one for, well, this is 0.5, so it doesn't matter which one you do, but you do the quality times the one for the gas, and then 1 minus the quality times the one for the liquid. And so this is 0.48. And this is cubic meters per kilogram. Any questions about that one? So if you know the quality, if you know the quality and you know the properties for the saturated vapor and the saturated liquid, you can always figure out the property for your mixture. And you can always go in reverse too. If you know the property for your material, for your mixture, and you know the properties for the saturated liquid and saturated vapor, you can calculate the quality from that. Yes.
Professor, will we need to do one of these like searching up table problems on the test on Friday?
That's a good question.
Will it be linear interpolation?
I'll keep that off of there. So it'll just be linear interpolation, and I'll just for the most part keep you from having to look at the tables much this semester. I'm just sort of I'm sort of thinking of that on the fly, but I'm just sort of switching over from making you use tables for everything to using just websites. Yeah.
In the exam, you said there is no linear.
There is linear interpolation, nothing that comes after it. I think that's what I said.
Yeah, you said up
Okay.
through linear.
Up through linear interpolation, so including. Question?
Yeah, what formula do you use for the last one?
What's the form of the equation?
Yeah.
That's the one that says for any property at saturation, the quality times the property as a gas plus 1 minus the quality times the property as a liquid gives you the property of the mixture. Yeah. And then part C, so refrigerant 134A at 1.5 megapascals and 100 degrees Celsius. All right, so this is a pressure and a temperature. So we can just look at the saturation table for this, and we can see, like, say for that temperature, is the pressure higher or lower than saturation? Okay, 100, 1.5 MPa. Saturation by pressure and temperature. So let's go to 100. So 100 degrees Celsius, and the corresponding saturation pressure is huge. This is point. Well, this is 39 times 10 to the fifth. We're talking about a pressure of 1.5 times 10 to the sixth. Okay, so we're talking about a pressure that's way higher. So the question is, if it's at a pressure that's much higher than the saturation pressure for that temperature, is this going to be a compressed liquid or a superheated vapor? What? It's actually going to be a liquid, and you can make sense of that if you think about this as a bunch of rubber balls bouncing around, and think of something going from liquid to gas as being these rubber balls bouncing out of this pit that they're in or whatever. Okay, and think about the effect of increasing and decreasing pressure. So the temperature is telling you how fast they're bouncing. Okay, and so the faster they bounce, the more likely one is to bounce out. But then pressure is holding it in there. Okay, and so if you have a really low pressure, then there's not much holding it in there, and these balls can easily bounce out. Okay, if there's a lot of pressure holding it in there, then they're really, even though they're moving fast, it's really hard for them to bounce out. And so this is still a liquid. It's harder for these balls to escape and become a gas. Okay, anybody have any questions about that? So now I'm going to take the lazy road on this because, well, let's look, and maybe there's just an actual value for this. 1.5 megapascals, 100 degrees Celsius. So let's go to, oh, we don't even have this for a liquid. Okay, well, so you could Google that or plug it into the website to find it. We don't really have a way to look that up here. Although, one thing we're going to talk about that I was planning to talk about today, maybe we won't get to this stuff, is that when something is a liquid, we can often treat it like it's incompressible. Okay? And for incompressible materials, for liquids, the specific volume is essentially constant. Okay? That's what incompressible means. The density is constant, the specific volume is constant. And so you can get a good, very good approximation for the specific volume by just looking at the saturation table at that temperature. So we go here, the temperature is 100. And use the liquid saturation. So 1.54 times 10 to the minus third meters cubed per kilogram is a very accurate approximation of what that would be. That's why they don't even give you liquid tables for this, because you can figure stuff out just based on saturation if you're assuming that something is something's incompressible. I didn't expect you to know that, obviously. And then let me just draw that. So we are talking about something over here. Okay. Let's see. So we've been talking about using tables and interpolation, and I gave you the website. So in a way, you can think of that as like, um, so knowing that wisconsin.edu website is all you ever need as long as first, the substance that you're investigating is covered by the website. And it covers a lot of things, but it certainly doesn't cover everything, and it doesn't cover mixtures. So, like, what if you wanted to do calculations for air with a specific amount of moisture and whatever? You wouldn't be able to use the website for that. Okay. For water or for popular refrigerants or for a bunch of other things, all you need is that website, but it doesn't cover everything. And second, also as long as the range that you're investigating, the range of states are covered by the website. So if their calculations don't go high enough for you for temperature or something, then you can't use it either. Okay. So what do you do in cases where you don't have that information? There are two important material simplifications. So material simplifications when you can't use the tables or the website. The first one is incompressible materials. And pretty much that's just referring to liquids. It's very unlikely that you would ever use a gas as an incompressible material. Incompressible materials, you can think of that as meaning that the density of the material is a constant, and therefore, equivalently, the specific volume is a constant. Okay, so think about water. So, like, as you go down to the bottom of the ocean, thousands of meters below the surface, the pressure gets unbelievable, almost to the point that human engineering, has a hard time dealing with that pressure, throwing everything we have at it. But even though that pressure changes a ton, the density stays pretty similar. Okay. So that's an incompressible material. And the second simplification is ideal gases. And so these are vapors where the pressure is not too high. And the temperature is not too low. Okay, so we're talking about very, very high pressures and temperatures. Almost always when something is in a vapor form, you can use the ideal gas law. You can treat it as an ideal gas. If you waited till the coldest temperature in Minnesota history, you know, and then put a gas in a piston cylinder and all of us stood on top of it to compress it down, that gas easily is still treatable as an ideal gas. Okay. So you have to be talking about really big pressures and really small temperatures. Before I introduce these simplifications, there's two things I have to introduce. So I need to define two things. One is enthalpy. And the second one is specific heat. Okay, so the first one is enthalpy. And what is enthalpy? I mean, I think really the short answer is it's just a mathematical thing that comes up in equations. We'll see when we derive certain things, this thing enthalpy just pops up. Okay. So don't think of it necessarily as like a physical thing that's defined because it's easy to measure or something. It's just a mathematical byproduct, I'm going to call it. So I'll call it a common mathematical byproduct. But if you like to have intuition about things, you can think of it as sort of roughly as the internal energy of a material plus the work required to make room for the material. It's defined. We use the letter H for it. And so the true enthalpy, the extensive enthalpy, is equal to the internal energy plus the pressure times the true volume. The units are units of energy, so the SI units are joules. And then maybe even more important to us is going to be the specific enthalpy. And we'll use lowercase h, and that is equal to the extensive enthalpy divided by the mass. And it's also equal to the specific internal energy plus the pressure times the specific volume. And this is a property that's in tables and websites. So for example, if the website covers, say you're doing a calculation for water, which the website covers, and you're dealing with a range of temperatures and pressures that the website covers. If you know like the temperature and pressure, you can plug those in and it'll tell you what the specific enthalpy is. And then if you need the true enthalpy, you can just multiply by the mass to get the true enthalpy. Okay, the next one is the specific heats. And there are two of them. They're defined in terms of partial derivatives. How many people here have seen partial derivatives somewhere? Half, maybe more. So these are defined using partial derivatives. It really isn't that important to understand what that means for the way we're going to use these. But I'm going to give you the partial derivative meanings. So the volume specific heat, the constant volume specific heat, CV, is defined as the partial derivative of the specific internal energy with respect to the temperature calculated for constant volume. Okay, that's a really complicated definition, and using this can get really complicated. It's not going to in this class, though. For anyone who hasn't seen partial derivatives before, if you've ever seen like a genius in a movie, they're always writing partial derivatives. This is what it looks like. So it's not just people being lazy about writing their derivatives. The curvy D's mean that it's a way to deal with multiple variables and derivative related things with multiple variables. But if you ever want to seem like a genius, like when your roommate comes in or whatever, be like writing partial derivatives on the window or the mirror or something. They'll know you're a genius. That's how they always show it in movies. And then the second one is the constant pressure specific heat. So C sub P. And that is the partial derivative of the specific enthalpy with respect to the temperature for constant pressure. When we use these, we'll use simplified versions of these. That hold in particular cases. How many of you have taken Physics 1 and had any kind of thermodynamics at the end of Physics 1? Okay, so yeah, you talked about specific heats, I'm sure, in Physics 1. You used it as a way to calculate a change in energy for a given temperature change of a material. And almost certainly you didn't use this partial derivative definition. You used a simplified form where it was a total derivative. And that's basically what we're going to do here. Oh, okay, we're out of time. I think you're lucky. I don't think we've gotten far enough for you to do any problems.